Recording is rolling. It is Tuesday, April 15th. So yesterday I started to tell you guys about this new topic, thermodynamics and heat transfer. So I need to finish that presentation. I have a whole stack of posters, which I gave you guys the thumbnails for back in January. So I will run through those at some point. And then we'll close the class with some Paul Hewitt demos. So yeah, it's a good lecture and demo type day. Okay. Now, one of the questions that has kind of come up closer to the end of class is going to be this question right here. So here, I'll throw this out, get a show of hands what you guys think, and then well, you'll see before we walk out the door today, if you're right. So if most materials, if you heat them up, they'll expand. Is that true? Like if I have a metal ring, is it true that the metal itself, suppose I got this fire flame right here. Does the metal itself expand? Yeah, right. Now this question says if you heat this metal ring, does the hole in the middle get larger or smaller, or does it stay the same size maybe? Right? So I'm not focused on the metal itself. I'm focused on this hole in the center. Does the hole in the center get larger or smaller or stay the same size? Let's see, show of hands what you guys are thinking right now. How many think you keep the metal ring? How many guys say the hole in the middle gets larger? Who says that? Who says the hole in the middle gets smaller? Who says it stays the same size? Ooh, all right, so I'm seeing different votes on each of those. So yeah, hang tight. You guys will see the answer to that by the end of class. But let's build back up to that. So I've got PowerPoint
is a source.
Go back to the beginning here. So first, give you guys a quick recap from yesterday, because I know it's a new topic. New things to think about. So we started with these different temperature systems, different ways to quantify how hot or cold is something. Nowadays, we have this kinetic energy theory of temperature, which has to do with how fast our molecules vibrating. Right? That comes from thermal energy, though, so there's a connection to that. Historically, Fahrenheit was developed first, then Celsius. But there are a couple equations later in this presentation. I'm thinking about the ideal gas law. I'm thinking about entropy, where you have to use what system? Kelvin. And what's special about Kelvin? Or you guys tell me, guys, what is special about Kelvin? Yeah, starts zero is absolute zero. So it's an absolute scale, as opposed to these other ones are relative scales that you go negative, but it's not like there's a negative of anything, right? So there you go. All right, so I bet you guys will apply that later in class today, and also yesterday in your notes. Let's use that. Right, there are these laws of thermodynamics. Went over these yesterday, but the main ones that I care about, if I ask any questions on this final exam that's coming up in a few weeks, is going to be on the first law and the second law of thermo. So first law, you guys know from last semester. It's basically conservation of energy. You cannot create or destroy energy. You're allowed to transfer energy into different forms. We have a new form this week, which is thermal energy. So you'll see that later today too. Now, the second law, this one's a bit more involved and abstract. This one says has a number of implications. It says here entropy always increases, say for an isolated system, for a closed system, for the universe at large. We did some calculations yesterday. That's to say that disorder in the universe, disorder increases. You could say that the unavailability of energy for useful work increases. So even though the quantity of energy stays constant, that's back to the first law of conservation of energy, the quality of energy in the universe decreases as time moves forward. And that's related to these spontaneous processes. So for example, you put a hot sink next to a cold sink, there's going to be a spontaneous motion of thermal energy from the hot to the cold until they reach equilibrium. So that picture on the left will spontaneously turn to that picture on the right. But you'll never see the reverse. If you start with that picture on the right, it will never spontaneously turn to that picture on the left. That's one of the consequences of the second law of thermodynamics. Right. Oh, right. Here's a disorder view of that. Right. So the sandcastle turned to pile of sand, but not the other way around. Again, spontaneously with the balloon. Right. All right. Here's these two formulas for the second law. So this one reads change in entropy. Isn't that what capital S is this week? Entropy. Okay, so like the amount of disorder, the unavailability of useful energy, okay, is equal to the energy transfer. That's what delta Q is, right? So change in thermal energy, right, divided by the absolute temperature that this happens at. So this is in your notes from yesterday. Say I've got some energy moved from this hot box to this cold box. The entropy of the hot box actually decreases because it's a negative delta Q. The entropy of the blue box increases because it's a positive delta Q. It's gaining the same delta Q, right? But they're going at different temperatures. We got a warmer temperature versus a colder temperature. So if you add up the differences in entropy, it always comes out to a positive value. Right? So the change for the red, the change for the blue, overall it comes out to positive. And that's true for the wider universe. And that's exactly what this bottom one says. It says the change in entropy over change in time is always positive, but it can never be negative. At least for large macroscopic systems, this is a probability law. Okay? We talked about forms of heat transfer, so conduction, convection, and radiation. You guys know those. Radiation is the only one that can go through vacuum of space. Convection, we have these convection currents in the oceans that have been set up over thousands of years. So the three main drivers. You guys tell me, because what's one of the main drivers that's causing these currents? Temperature differences. Yeah. What's another driver? Do you say like a salinity difference, like a saltiness difference, right? And then also wind, right? So those are three main. Do you guys see a little bit of Coriolis going on? You see clockwise in the northern and counterclockwise in the southern, right? Kind of, right? Change of latitudes. Right? I have a poster version of this that's geared specifically for water. Now, the slide you're looking at right now doesn't have any numbers on it, but we're looking at a phase change diagram for a temperature versus heat. Now, in general, you add heat to something and it rises in temperature. That's why this graph kind of goes up to the right. But that happens in steps. In fact, during these phase transitions, it actually flatlines. See how the temperature is stuck while it's melting or while it's boiling? Ooh. Now, what about the slopes of these lines? Do you guys think the slopes of these lines are different for different materials? Yeah, yeah. And then how about how long is this leg during melting or how long is this leg during boiling? Those would also be unique to each material, wouldn't it? Okay. So here's the equations that could describe that graph. So you read this as delta Q, that's the input energy, the transfer of energy. Delta T is the corresponding rise in temperature. M, guys, what does M stand for? Yeah, the mass, right? So it takes more energy to melt a large ice cube compared to a small one, or to raise the temperature. And then what is C? What is that? Specific heat capacity, right? Which I have a table of values for. You guys remember this table of values? Right? Did I ask you guys yesterday what's the largest number on that table? And you guys said what? Yeah, water, which is right here at the bottom, 4,186 joules per kilogram Kelvin. So that has to do with, if I go back a couple, it's related to the slope of this line. It's more like the inverse slope. So it takes lots and lots and lots of energy to raise the temperature of water just a little bit compared to other materials. It's easier to, here, if we go back a couple more slides, it's easier to heat that metal in that pot than it is the water inside. Right? Okay, so don't touch the metal, right? But the water. All right, and then what about this bottom equation? Ooh, guys, is there a delta T on this bottom equation? No, I don't see any change in temperature. If there's no change in temperature, what part of this graph is that referring to? How about this flat line where there's no change in temperature? Either the melting or the boiling in that phase transition. Right, so you put in some energy, there's your delta Q, to some mass, however many grams, whatever. Right? And this delta H, well, it could refer to one of two things, and that's this other table. Either specific latent heat of fusion if it's melting, or vaporization if it's boiling. Right? And there's the numbers for water. Now, I forget if we did this yesterday. Guys, take this ratio. What is the ratio of the energy that it takes to boil water compared to melt an ice cube? What is 2258 divided by 334? So we do that. You guys got calculators? What is that ratio equal to? What's 2258 divided by 334? Look at the water line right here. 6.7, is that about right? 6.7, right? What that means is that it takes about 6 or 7 times the energy to boil away water compared to melt the same mass of an ice cube. Right? Or if I look at back to this chart, you'll see it later today. If this was to scale for water, this boiling line would be about 6 or 7 times this melting line right here. Right? So you'll see that later today. So we'll get to that. Right. I think we got to about this slide yesterday. Well, most of my classes, and then the bell was ringing. This pressure and temperature map for different phases. Now, this is specific to water. Although, if you're a chemist one day working in a factory, you might have different chemicals you're working with, like tetra, what's it called? The chlorine water. And it might have a different phase of a map. So there's some special lines on here. We have a line at 0 degrees Celsius, 100 degrees Celsius. This room is about 22 degrees Celsius. That's room temperature, pretty close. Right? And there's a horizontal line at 101,000 pascals. That's 1 atmosphere pressure. So where my mouse cursor is, right there, that's where we're sitting in this room. So water should be in a liquid phase in this room. That makes sense, right? What if I wanted to turn that water into steam? Let's say boil the water. Now, the most obvious way to boil water is, I can put it on the stove and raise the temperature. That's going to the right of this graph. Okay, what's a different way to boil water without raising the temperature? Can you do that? You could do what? Lower pressure. Aha, you go straight down. Lower pressure, across the line straight down this way. Right? And that is, well, here. I got a reduced pressure boiling for you guys. Let me pull this up. Some of my classes I got to this yesterday and some not. So just go ahead and press video. Okay. So throw some water in the speaker, throw the hood on top, vacuum out the air, and then water is boiling. You guys see that boiling water? Let's see if you guys are following. If you put your hand in that boiling water right there, would it feel really hot or basically room temperature? Yeah, basically room temperature. Yeah, it wouldn't scald you. It wouldn't be hot at all. Right? In fact, that boiling process is actually taking energy out of the water and dumping it into the atmosphere. So what's left behind is actually getting colder. And what was that on top? That's a layer of what? Ice. Yeah, layer of ice. I think she'll turn this upside down and show you guys. Yeah, there it is, upside down. That definitely froze over some ice, right? Yeah, so boiling is actually a cooling process in the sense that if water is boiling, it's taking energy and dumping into the atmosphere. Now, of course, if you had that on a stove, the stove fire would be replenishing that thermal energy, right? But the temperature would be stuck on a stove. But yeah, in fact. How about this? Guys, can you go straight from a solid to a vapor? Is that possible? And what's that process called? It starts with an S. Sublimation. Do we say, do you guys know? I can think of one common material I know at room temperature can go through sublimation. And that's what? Huh? Uh, okay. Maybe we didn't get that part yesterday. Do you guys know dry ice? Dry ice? Right. They call it dry because it's never wet, right? It looks like an ice cube, but then it turns straight to a gas, right? Dry ice is not water. Guys, what is dry ice? Carbon dioxide. Aha, it's carbon dioxide. That's what it is, right? Oh, what about this special point right here? You guys see this triple point? Can you have a solid, liquid, gas all at the same place, same time? Is that possible? Okay. That's what this is right here. Here, go ahead and run this video. Hey, play this. There you go. Okay. Uh, I forget what material this is. It's not actually water. It's someone has a long name. I think it starts with the C. But there is a triple port for water. It's like triple right here. Now it's hard to hit the triple point exactly, like trying to balance a ball on the tip of a pencil. Right? So it's all like skirting like right around it and making little tiny adjustments to pressure and temperature just to try to hit that triple point. Okay? But if you can hit it, you can see some boiling snow. So see if you guys see some boiling snow right here. Ooh, look at that. Look at that. Triple point. It's a solid liquid and a gas all at the same time. Whoa. Whoa. Crazy. Okay. Ideal gas law. I think we touched on this a few weeks back, and a lot of you guys may have learned this in chemistry, so let's go over this. So this relates to the pressure, volume, and absolute temperature in an ideal gas. Now, N is, you can think the number of moles gas, number of molecules, basically how much gas is inside this balloon, if I'm looking at the balloon. This R is just a constant to tie everything together. Now, there's different values of R. I put two commonly used values of R down here. It depends what units you're working with, right? Are you working with pressure on pascals or atmospheres? That would make a difference. So different, right? All right. And there's a bunch of other ones too. I just put two. But what I want you guys to get out of this class or equation is that can you read the music of this equation? So how about this? What if this balloon was at 10 degrees Celsius and you warmed it up to 20 degrees Celsius? Wouldn't that be increasing the temperature? And if it's open to the atmosphere, then maybe the pressure is not really changing that much. But would the volume change? Because if you heat up a balloon, does the volume increase? Yeah. Now, if you go from 10 degrees Celsius to 20 degrees Celsius, is that doubling the temperature? Yes or no? No, because you have to convert to what first? Kelvin. Actually, let me do my calculator. Let's see. Let me flip the screen over here. So see what the temperature is. So if I go from 10 to 20, so if I do 20 degrees Celsius, I have to add 273. So that'd be 293 Kelvin, wouldn't it? Okay. Close parenthesis, divide by open parenthesis. What's 10 plus 273? Okay. So the ratio of temperature actually went by a factor of 1.035. Do you see that? Increased by about 3.5%, right? In an absolute sense. Guys, if the temperature increased in an absolute sense by 3.5%, then what can you say about the volume of the balloon? It increased by how much? 3.5%. I said it's 3.5% bigger. Right? It's not twice as big, it's 3.5% bigger, right? How about this? What about the relationship between pressure and volume? Suppose you had temperature locked in place, right? But you squeeze on the side of the balloon, and you get it down to half of its original volume. Because if it's half the original volume, what would be the pressure inside the balloon? Twice as much. Yeah. Wait, 2 times a half balances out for the same temperature. You see that? Right. Yeah, so there you go. Any questions about ideal gas law? All right. Okay, so some of these slides, that's what I'm missing. All All right, well, okay. We're gonna flip over to posters for a while. So these are your thumbnail notes I gave you guys back at back in January. Here, go to the poster side. So got three temperature scales. Now, what's the conversions from one scale to another? I got a couple of equations for that. Here's Celsius to Kelvin, just add 273 and change, but I normally just ignore the change. Okay. No, they're scaled the same. You guys see that? There's no factor on the temperature Celsius. Is the change of 100 degrees Celsius the change of 100 Kelvin? Is that the same change? Yeah, it's the same. Okay. So if you're talking about a change in temperature, actually it's okay to use either one of these in equations because the change is still the same. Right? But Fahrenheit, it's more like a factor of pretty close to 2. It's like 9/5. You guys see 9/5? Okay. So suppose you go vacation in England and say, "Oh, it's a jolly 19 degrees outside." Yes, yes. And say, "Oh, what is that in American? Guys, what is 19 degrees in Fahrenheit units? What is that?" Here, I'll do it. You guys do it. So we get the same thing. What is 19 degrees? What is that? What do you guys get? Did you guys do? Did you guys do 9/5 times 19 plus 32? Yeah. What did you guys get? What is my calculator messed up? You guys are saying something different from me. Hold on. I'm gonna reset this thing. Reset. Make sure. I don't know why we're getting different numbers. All right, so 9/5 times 19 degrees, I said? Celsius plus 32. Oh, wow. Okay, yeah. No, you guys are right. Okay, I think this calculator is glitching. Yeah, 66 degrees. There you go. All right, so that would be in Fahrenheit work. All right, so you guys can convert. Okay. And if you want to go the other way, of course, you can do that too. So you could, if you start with Fahrenheit and want Celsius, you could subtract 32 and then times 5/9. Okay. Also, this is pretty close to a ratio of 2. 32 is pretty close to 30. So if you didn't have a calculator, you do times 2 plus 30. It'd be pretty close to. All right, so we got that. Laws of thermo, again, the main ones I care about are first law, which is conservation of energy, and second law, which is increase in entropy as time moves forward. So this is like a like arrow of time, spontaneous processes. Sorry about this. All right, I've got a few posters for different thermodynamic processes. Now, these aren't all of them, but these are some common ones. So Carnot cycle is famous because it's considered the most efficient of these thermodynamic processes. Suppose you have a hot sink and a cold sink and like some piston in the middle. Okay? There's a Rankine cycle, which is how electricity is generated. And there's Stirling engine, which I have one of those right here. And also I have a video for you guys. So we'll go these. Right? There's some that I don't have. There's an Otto engine, that's OTTO. That's how your gasoline car drives. There's a diesel engine if you have diesel in your car. So, right. Right, so let's look at these a little bit. Now, so I got a hot sink next to a cold sink. So I guess there's some thermal energy traveling from the hot to the cold, right? And suppose you have some kind of engine in the middle. It's like a Carnot cycle, Carnot engine. I have a pressure versus volume diagram to explain the story, and also temperature versus entropy. Now, this particular cycle, this first one here, I don't know if you guys can read, it says isothermal expansion. Iso means same, thermal means temperature, so same temperature. You see these two temperature curves? I got this hot temperature and this cold temperature. That's like a hot sink and the cold sink. So this step right here corresponds to this movement right here. So it's expanding volumes, that's pushing the piston up, and the same kind of pressure is going down. So isothermal expansion. Then we get adiabatic expansion, that's from here to here, crossing this line. Then isothermal compression, so that'd be like decreasing the volume, increasing pressure. And finally, adiabatic compression, takes you back up here, and it's a closed loop. And here's the temperature versus entropy. Now, some parts the entropy increases and some parts it decreases, but if this is ideal, then there's hardly any or maybe zero entropy change on that. So I kind of mention there. Rankine cycle, here's how most electricity is generated. Whether you have coal or natural gas or nuclear, it's some version of boiling water. Now you have all that energy is in the form of steam. It's going to force this turbine to turn, which you guys remember from last week. Isn't that just forcing a wire past a magnet? Now the energy is being converted to the electric grid. Right? Remember, no energy is ever being created. It's just being transferred, say, from the coal to the steam to the electric grid. Right? Now, what leads the turbine is relatively cooler steam that's been depleted of its useful energy. So you run that through a condenser to cool it down to a liquid. Now it's still a really hot liquid because by the time you boil it, you don't want to have waste a bunch of energy bringing it up to a boiling point here. Right? So maybe like 95 degrees Celsius, and then you boil it, and round and round it goes. Right? That's how you get energy from coal or nuclear. Okay? And temperature versus entropy is the area, that right there, area under the curve tells you how much energy goes onto the grid. Right, here's your Stirling engine, which I'll show you guys a video for here. No, actually, the video works better than the one in real life, so I'll just show you guys the video. But if I have a cup of hot water here, what it's going to do is it's going to heat up this air right here. It's going to push, you guys see this piston right here? Yeah, push this piston up. Right? And there's like a second piston, right here, it's a little hard to see. Right? That would turn this wheel. So hang tight for that. Show you guys that one real soon. Okay, entropy. Here's your two entropy equations I care about. So change in entropy is the thermal energy transferred, delta Q, divided by the absolute temperature this happens at. In your notes yesterday, did we run through a couple of these in your notes yesterday? Okay. There's a hot sink next to a cold sink. So the hot one actually decreases the entropy, the cold one heats up a little bit. But if you add those differences together overall, you get this equation on the right, which is that overall, as time moves forward, so the rate change of entropy for the entire universe as a function of time, it always increases. Okay. So everybody right? Maybe I should say greater than or equal to account for, say, a Carnot engine, so like that. Okay. Speaking of engines and engine efficiency, how efficiency is an engine? So suppose I got hot sink to cold sink. What if there's 100 joules that's leaving this hot sink? And suppose you have an engine in the middle, maybe like the Stirling engine, and it gets it to move. Right? See, if I have a cup of hot water underneath, the cold sink would actually be the entire atmosphere. So the thermal energy is going from the hot cup of water to the atmosphere. See that same? Okay. Suppose I capture 20 joules out of this 100 joules. So 100 joules leave, 20 joules are converted to useful work to make this this wheel rotate. Okay. What would the efficiency be? Who can tell me? 20%, right? 20 divided by 100, right? 20 joules over 100 joules. Okay. This is Greek letter eta, which stands for efficiency in this case. Okay. And then the other 80 joules goes to heating up your cold sink. Right? Okay. Now, if you have specifically a Carnot engine, there is this Carnot, I should say ideal efficiency for a Carnot engine, right? Which is 1 minus the ratio of the temperatures. Let's see if you guys can solve that. I want to see. Let's try this out. Suppose I give you guys got a calculator? You guys ready for this? Suppose I give you a cold sink of, 10 degrees Celsius. And I give you a hot sink of, how about 90 degrees Celsius? Okay. And I want to know, suppose I put a Carnot engine between these two sinks. I have a Carnot engine. Okay. And I want to know what's the maximum efficiency of that engine. So I'll solve it. You guys solve it. Let's see if we get the same thing. Here's a hint. Do not say 89%. The answer is not 89%. If you got 89%, then you're forgetting something. I give you guys that much of a hint. Okay. Who got something other than 89%? Thinks they got it right. What'd you get?
9.75.
So somewhere between 0 and 1 is a decimal. Okay. I got something different. Who else got a number? What's the efficiency of that engine right there? The maximum ideal efficiency. Here's a bigger hint. Guys, can you go plug in Celsius into here and here? I think you got to get it now. How about now? Who's got it? How about now? Huh? Alexander got it. 22%. That's what I got. I got 22% efficient. Okay. So let's write this equation. So efficiency is, okay, so 1 minus ratio of the temperatures. I said 10 degrees and 90 degrees Celsius. So it's be 10 plus 273. And then 90 plus 273. Would it be like that? Is that true? Right. Which comes out to 0.22, or you could call that 22% efficient. Okay, 22%. Okay, guys good? 32%. Okay. Okay. And then here, play around with this formula too. Like, here, read the music of this equation. It turns into sort of equation animation. What if your cold sink approached absolute zero? Could this fraction approach zero and your efficiency is approaching 100%? But it'll never quite reach 100% because you can't ever quite reach absolute zero. Okay. Or what if your hot sink was incredibly hot? That would also make this closer to 100%, wouldn't it? Okay. What? Oh, how about this? Guys, what if the temperatures are the same? What if I have 20 degrees and 20 degrees. Guys, what would this ratio be equal to? 1. What's 1 minus 1? 0. Now your engine never even runs. You guys see all that? See all that? All right, here's your heat curve. All right, now this one on your poster, I did scale proportional to the numbers for water. Well, at least some of these lines are. Okay. So somebody tell me. I bet somebody knows the answer. You guys see all this energy it takes to boil away water? And this energy that it takes to melt an ice cube? I suppose it's the same mass. Like I got 10 grams and 10 grams. Who could tell me, if I measure this with a ruler, how long is that line? And how long is this little short line down here? What's the ratio of this length to this length? About 6.7. That's right. Okay. Because can you guys take 2265 divided by 334? Okay, so it takes way more energy to boil the water than it does to melt an ice cube. All right, so we got that. Water. Okay, here's your pressure, temperature, phase diagram. Yeah, for water. Okay, so this looks a lot like what you guys saw on the slide. Okay. Ooh, Newton's law of cooling. Suppose you have a hot cup of coffee and you just leave it out in the atmosphere for a few hours and come back a few hours later. Is this temperature? I got a thermometer in here. Is this temperature going to eventually reach room temperature? Yeah. Okay. So if you made a graph, temperature versus time, so reading off this thermometer, the rate of change actually slows down over time as it asymptotically approaches the environmental temperature, which is room temperature. Okay? It's called Newton's law of cooling. I've seen a couple different formulas for this, and this is one. This is the rate change of heat transfer. That's dq over dt. So how fast? But that's dependent on all these other variables. Like, what's the difference in temperature between, say, your cup of coffee and the room? Okay? And as the temperatures get closer together, doesn't this difference approach 0? Which means that this whole process slows down, doesn't it? Okay? What do you guys think this A stands for? It's a word that starts with A. Area, like surface area, right? Because what if you have like a little ball of coffee versus like a pan of the same amount of coffee? Right? Would the wide pan with the large surface area exposed to the environment cool down a lot faster? Yeah. It's like 3 times the area, it'd be 3 times as fast. How about this H is a material property. So if you had a cup of coffee versus a cup of olive oil, I think this would slow down different rates. That's all embedded in that H right there. You guys get that? Okay. All right. Okay, here's specific heat capacities for different materials. If you use any number of class, I think we used this one recently, 4.18 kilojoule per kilogram Kelvin, or sometimes you see it as 4,180 joules per kilogram Kelvin. So different versions of that. Okay. It has to do with how difficult it is to heat up liquid water. Ooh, this one's fun. I figure out what to do with you guys the rest of the week, but I might throw some puzzles at you guys. And if I do, this is a fun puzzle. What if you take a hot piece of metal and drop it into a beaker of water? Now, is the metal going to cool down? Yeah. Is the water going to warm up a little bit? Yeah. In fact, what kicks off this process, the first line, is that the amount of thermal energy exported by the metal is exactly imported by the water, as long as it's a closed system. Wouldn't that be true? Okay. This metal is radiating out, or maybe it's conduction, I should say, right? Okay. So it's losing thermal energy, and the water is exactly picking up the same amount. Right? Okay. And isn't this process going to continue until they reach equilibrium temperature and the same temperature? And then we're back to the zeroth law. And it stops. So what is the equilibrium temperature? How do you go from this step to this step? All right, well, we'll see. What would be the middle steps? So the transfer of energy, isn't that MC delta T? Okay, so mass times specific heat capacity times the change in temperature corresponds to the transfer of thermal energy in joules. Right? And what's what's imported by the water that comes from the metal, so it's exported by the metal, those have to be the same. Okay? And then if you know the numbers, it's like if you know how much mass water, how much mass metal, if you know specific heat of water, you guys know it's like, what is it, 4.18 joules per gram Kelvin, something like that. And then for metal, well, what type of metal? We're talking about zinc, copper, because those would have different specific heat capacities. Right? And then this delta T, you can replace with final minus initial temperature. Okay, and then you can solve for final temperature, which is equilibrium temperature. Right, you guys get that? Okay. How about this? Because what if you dropped a hot piece of metal into the Atlantic Ocean? Is the temperature of the Atlantic Ocean going to go up in a measurable amount? No, because the mass of water would be so ginormous compared to the mass of metal. Okay, so you guys can kind of navigate that idea. So, some of these big ideas I want you guys to get out of this, even without any numbers. Like, okay, I see how the universe works. Right? Ooh, here's another fun puzzle. I think this one's a little easier. So, you guys think if you have a waterfall and you measure the temperature at the top and the bottom, you guys think, where's the water a little bit warmer, at the top or at the bottom? At the bottom where it's going to splash, right? Because do you think that a bunch of this potential energy, which starts out as mgh, converts into thermal delta Q? So this is conservation of energy. That's what this is. Sum of energy before equals sum of energy after. So the top and bottom, same energy, right? But now we have a new form of energy, which is thermal energy. So this mgh turns into Q, which is thermal. Right? And Q, you guys know, is mc delta T. So you can get a temperature rise. Right? Now look at the final result here. Let's read the music of this equation. This says the stronger the gravity field, isn't that going to accelerate the water faster? That would raise the temperature more. Right? Or is it? How about the taller the waterfall? The taller the waterfall, the more the rise in temperature. But doesn't water have a really, really, really high specific heat capacity? Wasn't it like the largest number on the table of values from yesterday? Which means it's really hard to change the temperature of water. So if you're dropping olive oil down, I bet it would be easier to heat up olive oil with this method than it would water, because water is really stable temperature. Right? You guys see how that? Right. And here's the last poster I got for you guys: refrigeration process. Now, I know my parents tell me when they went to school back in the day, they didn't even have air conditioning, and that's what this is: refrigeration, air conditioning. It's the same technology. So yeah, lucky us, we live in well, time we do now, I suppose, for this reason. Yeah. So let's go through this process. Now, the main part of the process that you care about, I guess, why would you buy a refrigerator or an air conditioner, is this part right here, where you have some warm air and you want to cool it off. So if you have this refrigerant that's cold, it's going to absorb heat energy from the surrounding environment, and the air that runs over it is going to be relatively cooler air because it's lost some thermal energy. And there's your refrigerator right here. Here's your refrigerator box. You guys see that? Here's your air conditioner. Okay. But there's a larger picture to consider for this thermodynamic process. So the rest goes like this. Now you have this warmed refrigerant. It goes through this compressor and is routed into this condenser. And this condenser is where it releases this thermal energy back into the atmosphere. Remember, conservation of energy still applies. You have to dump that thermal energy somewhere. So let's dump it into the atmosphere. And then now we've cooled this refrigerant. So let's route it back through this expansion valve. This path, it's going to be a liquid form. Right? And then round and round it goes, and it's a cyclical process. Right? Okay, so do you guys remember yesterday, if you have a hot box next to a cold box, they'll spontaneously reach the equilibrium temperature, but not the other way around. Right? And I think I mentioned you can take room temperature air and you can force it to be cold and separate out the hot from it. Right? But this is not a spontaneous process. Isn't this an energy intensive process? Right? So let's go back to this PowerPoint right here. Refrigeration. Who's ever walked down an old area of town, maybe some building that was built 100 years ago, and you see all these condenser units hanging out the windows? You guys ever seen something like this? Yeah, yeah. Now, why? Or maybe you at home, maybe you have central air conditioning, but if you go outside, you see the condenser outside, right? Guys, why does this have to be out the window? Why not just put everything like right in the middle of the room? Okay. Good. Let's answer this with a different type question, which is actually kind of the same question. Right. Let me give you guys a question right now that I'm almost certainly going to ask you on the final exam. First, in the morning, you open up the refrigerator, right? And then you forget to close the fridge and you go to school, and the refrigerator door is just left open all day, and just cold air dumping out the front of the fridge. You come back at the end of the day. Is your house at the end of the day really, really cold or really, really warm? Really warm. Exactly. Because here, let's see the full process. That's half the process right there. Let's see the full process. Here's the full process. Here's all the cold air dumping out the front of the fridge. Shouldn't that be cold in your house? But don't forget, if you reach back behind the fridge, there's all this hot air dumping out. Or in the case of an air conditioner, this is the condenser unit over here dumping out all this hot air. And if you just have the whole system in the middle of a room, then, well, at best it would be a wash and it wouldn't change the temperature at all. But in reality, since this is not a spontaneous process, you have to have your fridge or your air conditioner hooked into the outlet. You're importing energy. This hot like beats this cold over here. It's kind of a colloquial way to say that. Okay, so overall, it's going to warm up the room. Right. So everybody okay with that? Right, there you go. Is that all I got on this PowerPoint? I think. Oh no, we got Bill 9.
Let's say this beaker full of very warm water is a source of heat. Here's a special type of engine. A Stirling engine named after the Stirling brothers who invented it, got a patent in 1807. The heat from this water is warming the bottom plate of this engine. Give it a little nudge. The engine will run. Now notice there are two pistons. There's this little one up here, the primary, and then there's this big one down here, the secondary. And as the heat from this water warms the bottom plate, it makes the air expand. The expanding air drives the piston. So this is a way to convert the energy of heat into what we call mechanical work, or making something spin. And the extraordinary thing about Stirling engines is they're so efficient. It's just a little bit of hot water. And look how fast it's making the wheel go. Now watch what happens when we take the same Stirling engine running clockwise and put it on another beaker, but this one's full of ice water. In just a few seconds, the Stirling engine will slow down because it's lost its source of heat from the bottom. But now it will run the other way from the ice. So there's an old joke in science. A thermos bottle keeps cold things cold and hot things hot. How does it know? Well, the reason it knows is because, in a sense, in science, there's no such thing as cold. There's only the absence of heat. So this is still a heat engine, and it's running off of heat. But the source of heat now is the room. The air in this room is warming the top plate, and heat is now flowing down through the engine instead of up through the engine as it was over on the source of hot water. Now, Stirling engines have been proposed for all sorts of things. In the early 1800s, they were used to pump water all over the place. People have talked about putting them in cars again. But the tricky thing about a Stirling engine, they're hard to speed up and slow down. The great thing about a car engine is you can speed up and slow down very easily. You've probably heard of a diesel engine. That's named after a guy named Diesel who invented the process. Then your car that runs off gasoline has the Otto engine, O-T-T-O, another German scientist. There's all sorts of heat engines. There's the Watt engine, the Rankine engine, the Brayton engine, the Atkinson engine. And they're all different arrangements of pistons and valves to convert heat into mechanical work. It could be that the Stirling engine is going to make a big comeback because it's so efficient. And maybe you'll be the scientist or engineer who finds a way to use it in extremely important application.
Brownian motion. You guys be reading about what Robert Brown did back in 1830. He's looking in a microscope. And in the microscope, he sees little things jiggling. And at first he thought it was something in there alive. There's little particles of soot. And these little things are jiggling, jiggling, jiggling. And Brown thought that maybe he saw atoms. But they weren't atoms. Guess what they were again? Little specks of dust banged into by, guess what? Atoms. It's like this. See this styrofoam cup? You guys can all see this. See this little BB right here? Little BB in my hand? I got a whole bunch of them there, see them? I'll spill them on the table. See all those BBs? You guys can't see those BBs because you're too far away from them, okay? But can you picture this? Can you picture the styrofoam cup on the table and all these BBs all moving around haphazardly, chaotically, and every once in a while the BBs, more BBs hit one side of the cup than the other? What would the cup do? Wouldn't the cup start to jiggle? And you guys can see the cup, but you can't see what's making the cup jiggle. You know there's something smaller than you can see is making the cup jiggle. And that's what Robert Brown saw in his microscope. He saw little particles big enough to see jiggle. Why jiggling? Small enough. There could be more atoms on one side than the other. A little bit more net force on one side than the other. Boom, that thing will jiggle around. So in response to the jiggling atoms, boom, the visible observation, microscopic particles moving. Brownian motion. So any one person's one breath. You guys got atoms from that breath right now. Now, usually people take more than one breath. Leonardo da Vinci, the old dude, took many, many breaths. And all his breaths You have hundreds of billions of atoms of Leonardo da Vinci's breath in you or any other person who lived for a long time. So you were made up of the atoms of everyone who was ever before you. How many people in the world today? About 4.5 billion. That's 4.5 times 10 to the 9. How many people compared to how many atoms in your lungs? Which is bigger? You know, there's a lot of people. People at 10 to the 9. Atoms at 10 to the 22. How many people have been on the planet since the beginning? Nobody knows. But Arthur C. Clarke has made an estimation, and he said it this way: behind every human being stands 30 ghosts. That 1/30 of the human of all human race from way back is walking the earth today. That number's changing quickly. Let's say 1/30. So that means there are 30 more people on the earth from time zero than there are now. Now there's about 4 billion. And there's 30 times that number for the total number of people that ever lived. 3/4 of 12. Call this 100. That's like 10 to the 11th. 10 to the 11th is 100 billion. So 100 billion people in the world. But the number of atoms in your lungs, 10 to the 22, what's that? Billion, 18. 10,000 billion atoms in your lungs. So many more atoms in your lungs than people that ever lived. So you can be rest assured that inside your lungs or inside your body at any moment are atoms from every human being who ever lived. And let's talk about this expansion and this expansion under different temperatures and everything. We got something here that's kind of neat today. Ted, could you give me a hand? Talk about low temperatures. Ted's brought over here some liquid nitrogen. This liquid nitrogen is about 190 degrees below 0 Celsius, really cold. Almost 80 degrees above the absolute 0 temperature. Now, can we have a volunteer jam their hand in there for about 5 minutes? Okay, nobody gonna do that, right?
What do you want to do first?
Okay, let's show how the let's show how the volume of something will change. Here's an air-filled balloon, gang. Okay, what's going to happen to the volume when it gets cold? How many say, oh, it's going to expand? Stand up. And what happens to the volume, gang? Yeah. Now it's going to start to warm up to air temperature. What happened to the volume? What happened to the volume? We bring it above air temperature? Bring it a little closer, Ted. Yeah. Let's try the flour. Here's the flour Ted found out in the ground. It's kind of nice and limp, right? Kind of limp, isn't it? Okay. But what happens if we slow those molecules down? Yeah, why did it fizzle like that? What's going on? Oh, gang, did you see such a thing? Yeah, right now, it goes through. With a little effort, it goes through, yeah? I'm not gonna take the time to heat up the ball. I'd waste your time, because you know the ball would get bigger and no way it would go through. I'm gonna heat instead the ring. You get that ring nice and hot. Is the ring expanding? Yeah, it's expanding. How about the hole? Is the hole expanding? See, a lot of people think this. A lot of people reason that the hole is it's gonna expand this way and expand in this way because the ring is gonna get fatter. Will that ring get fatter? Turns out it will. So they think this part will expand out here and this part in here and the hole gets smaller. But lo and behold, it's appreciably bigger. So the hole does get bigger again. If we take our ring and we cut it up into 4 pieces, gang, 4 pieces. And if I put any one of those pieces in the oven, would it get bigger? Would it expand and maybe look like this? It's going to expand and look like that. And this side here is longer in an expanded state than like this. So take them apart and look at it and you can kind of see it. Or take your ring and open it up like this. Is it going to get fatter? Yes, it's going to get fatter. So it expands out to here maybe. Out to here maybe, yeah? But that's not the end of the story. You see, we're so busy thinking about what happens like this, huh? That we forget it's expanding this way too. And it expands lengthwise as well. And lengthwise, we see it expands out to here. And I submit to you that this dotted line on the top is longer than the solid line below. And that dotted line on the top represents the new inner circumference. So every part of the ring, the thickness, the width, circumference, outer, inner, everything expands by the same rate if the heating is uniform. And it pretty well was here. So the hole gets larger, okay? You've got a jar of peanut butter, you can't open it up. You give it to a muscle-bound type, still can't open it up. So what do? And hand it to you. You take it over, put it in the stove upside down momentarily, or put it under the hot water. Doesn't that metal lid expand? Does that make it tighter against the glass or looser? Looser. And hey, mind. Hey, bronze one thing, wonderful, but the mind too. So you think, and you can open it up by just heating it up. Turns out the whole darn thing will expand, whole and all. Hi, gang. Thermal expansion time. Here I have what's called the bimetallic strip. It's a strip of metal consisting of 2 kinds. Brass on one side, steel on the other, welded together. I'm going to heat it up. Looks like it's bending. It's bending because one side's expanding more than the other. If I take this and turn it into a coil and heat it up, it would shrink. Or cool it, it would expand. That would be a thermostat. So some things conduct better than other things. Piece of wood, very, very good insulator. This wood's a good insulator at any temperature. This wood is a good insulator even if it's very, very hot. You ever reach in a frying pan and pull out of the frying pan, maybe it's up to 400 degrees Fahrenheit, you're gonna cook some food or something, you got a frying pan in there and it's all iron. Ever be reaching in with your bare hand and grab the iron pan? If you ever have, you can show that today, you'd be tattooed, right? You're gonna burn yourself, isn't that right? But could you reach into that oven and grab a pan if it had a wooden handle and grab it momentarily? You can do that. You can do that. You know why? Because that wood is hot. It has the same temperature as the metal, but not very much energy is going to conduct from the wood to your hand. So you can safely hold it. You can do that. You ever see these people walking on hot coals after they've paid more than $300 for some sort of a course that teaches you how to have self-confidence in yourself? And then the test of that self-confidence is they say, we are going to violate the laws of physics and show you that mind over matter, that $300 you've spent for that 15-minute session is going to pay off because we're going to apply those techniques and we're going to show that you can walk with bare feet on hot coals. And so the people do that. They take off their shoes, bare feet, they step on the hot coals, they walk across, and they think they have violated physics. Gang, those are hot coals of what? Wood. And that wood is very hot, isn't it? How much of that heat in that wood is going to get to the feet? What does it depend upon? Not only the temperature of the wood, but something else. Begin with a C, end with conductivity. See if you can put it together. What is it, gang? The conductivity. And the conductivity of the wood is good or not so good? Not so good. So when you step with your bare foot on a hot coal, there's a heat transfer. A lot or a little? What's the answer begin with, gang? Okay, L, okay, so it's a little L, right? And so only if that's really, really neat, only a little bit of heat will get to your foot. And you can what, now you're not gonna stand in one place there, okay? You're not gonna reach in that oven and hold, just hang on to that wooden handle, and you're gonna be hurt. But you can grab it and pull it out, boom, and you can step across red hot coals of wood without harm. It turns out that air is a good conductor or poor conductor. It turns out it's a poor conductor, and aren't you glad? Because what if air were a very, very good conductor? How would you feel all the time? Begins with a C, ends with old. Put it together, gang. You would feel cold. Let's suppose the air were as good conducting as like a piece of metal. Do you ever stand on a nut at home and lean up against a metal door? Woo! It's cold to the touch. But that metal door has the same temperature as the air around you. So be glad that air is a poor conductor and a good insulator. In fact, when you want to keep yourself warm when you're going to go camp and that sort of thing, don't you get a down-filled sleeping bag? What's all the down for? It's holding air in one place. It keeps the air from circulating. And that down will just hold the. How about animals? You wonder about the animals. How do they make it up in the snow-covered mountains? They're covered with fur. And that fur puffs up, and guess what it holds inside? Begins with A, ends with R. Air. And that air is a very, very good insulator. So most of the things that keep you very, very warm in a cold climate, like that which insulates, like styrofoam, yeah, or spun glass, or things like that. They're all what? They're things that hold air. See these the thermal underwear they have now? The thermal underwear, you look at the thermal underwear and all this is like a net, like a fish net, and you put that on, that's going to keep you warm. But over that fishnet underwear, you put a regular t-shirt. And now what's trapped between your skin and that t-shirt? Begins with an A. All right, ends with R. Air, okay? And can that air circulate? No, if the air warmed up and just went away, then you get cold again, see? But it's all held there by the little netting. That's what it is. When that stuff first came out, I looked at that and said, what? Because, this is going to keep you warm, honey. And they show you something with all these holes. Say, all these holes? That doesn't sound right. But wait a minute. I know what that is. It begins with a P. It begins with an F. What is it? Oh, you don't be knowing. Physics.
All right, it's about time we got for the close on today.